So dear friends, we are continuing our talk on the issue of the different level of material structures and so their relations with the material properties. If you remember, we are talking about the crystalline structure this time, and so in the previous lecture we figured out that all crystalline materials are arranged in some very special 3D order in the special crystalline structures. The number of these structures are not infinite. We outlined 7 different crystal systems, and in this lecture I will just give you some examples of the relations between the material properties, including physical properties and mechanical properties, with this level of structure, crystalline structure. So we can start from the very beginning asking a very simple question. What are the level of material structure are? And if you remember, so we talked about atomic structure when the scale is on the order of 1 angstrom. And now we are talking about the crystalline structure, which is on the order of, let's say, 10 angstroms. In some sense, we are in the scale of the nano structure of the material. So let's ask the next question is what is material composition? And the simple answer of this is that the chemical makeup of materials, or so elements which we can find inside our material, in some sense define the material composition. So composition can be very simple. It can be just carbon, or it can be binary phase such as boron nitride, or it can be extremely complex as the lanthanum-based perovskite shown in this screen, which involves about 5 elements. So of course we can find out other materials which consist of 10, 15, 20 different elements. This is material makeup. So that's easy to understand. Now the question is, so again, what are the material properties? And we already discussed that somehow we can subdivide these properties on the mechanical property, which describe the material can withstand applied forces, including tensile or compressive forces, impact, cycling, or fatigue, and so on and so forth. The physical properties, the other type of properties, so which describe material characteristics such that not so closely related to the applied load, such as we discussed, let's say color, as electrical and thermal conductivity, optical property, and so on and so forth. So, or as we discussed in detail in the previous lecture, melting point of materials. So the next question can be the follows: is that can material have some composition, same composition, but possess different properties? And the answer is, of course, yes. And you can give me very many examples of that. For example, if we take just carbon itself, it means that the makeup of the material is just one element with one specific electron structure, as we know from the atomic physics now. And however, so we can distinguish now different types of materials made from carbon which do have extremely different properties. So on this screen, so we can see, for example, the graphite itself, and which has, as you can see, let's say black color. And then you can see also your famous diamonds, which are transparent completely, colorless, no color at all, also consist only from carbon, as you know. Finally, we can see here now the Bucky structure, which does have the red color. So same material, same makeup, extremely different physical property, such as color. Of course, we are not talking about the other properties immediately which come to your mind, let's say hardness of the material. You know that, so the diamond is the hardest material which you could find in nature, while graphite is not hard at all. So it means that indeed materials may have absolutely same chemical composition, absolutely same, so it can consist of absolutely same elements which do have absolutely same the electron structure, atomic structure. Okay, so now the question is why it could be so, and you know the answer to this question, of course. So the materials, they involve millions of atoms, maybe of the same nature even, but which can be arranged in absolutely different crystal systems, and these crystal structures in some sense define the material property. For example, indeed, so the graphite, you can see the hexagonal structure of the graphite here is very different, thank you, is very different as the cubic structure of diamond. This is versed cubic structure, which does have much more higher atomic density inside, and as the result, extremely different properties. So the other example you can see on this screen. So what we are talking about tin. It's a very well-known element, and so tin at room temperature typically so does have the tetragonal crystal structure, pretty dense one, and this material is ductile. It's metal actually. It's a ductile material, it's conductive material, whatever can you expect from the metal type of atomic structures. However, it is known that it's about 13 degrees of Celsius under cooling. It can relatively fast transform to the so-called gray tin, and as you can see on this slide, on this screen, so it is again the diamond type of cubic structure, not so dense actually as compared to the tetragonal structure, and immediately all properties of material changes. So now we are talking about the brittle covalent type of behavior of the material as the result. So it's not so great conducting property, it's semiconductor now, and so this very fast change of crystal structure of material again leads to the significant change of its property. And moreover, it's interesting that so if you at this lower temperature so put in contact the gray and white tin, the white tin will start to transform to the gray one. That's why this phenomenon has this specific name, tin plug. So we have discussed the changing of physical properties of material as a function of their crystal structure. Now let's come back to the mechanical property. So before we discuss elastic mechanical property of materials, and we applied not so big load of the material in order no any let's say destruction of the material inner structure takes place. However, as you know, we can apply it much more larger load, and at some point so the bond stretches in the crystal structure, and the planes share, and again at some points even so we do have destruction of these bonds. So in this case we are talking not about elastic but about the plastic permanent deformation of the material. So again, coming to the stress strain diagram, we have to go to much higher let's say strains, and you can see that so at some point the elastic strain is equal to 0.2%, and this applied stress is so-called, let's say, yield point or yield stress of the material. Also by increasing applied stress, we can reach the maximum of this dependence, stress strain dependence, which correspond to the tensile stress, and so on so far. So let's talk and let's see how the crystal structure of the material can govern, can control the plastic deformation and the plastic properties of the material. So in order to understand that, we have to refresh our mind and conclude and agree that there is no ideal material. All materials, they do have some kind of defects. And one of the main defects which defines in some sense mechanical property, especially for metals, so is edge dislocation. On this screen, you can see edge dislocation. So we do have the extra half plane on the upper part of our crystal. And so this dislocation, in some sense, is defined by the Burger vector, which defined the magnitude and the direction of the dislocation. And for this edge dislocation specifically, the Burger vector and dislocation line, they're normal to each other. So again, so assume that we do have some extra half plane in our material, which is the edge dislocation defects. So it was shown experimentally then when the shear force is applied to material, so these dislocations, they move. And so the plastic deformation of the material occurs not for the complete destruction of the atomic bonds along the whole cross-section of the material, but because of the slipping or the motion of these defects of this kind of dislocation. So next screen just demonstrates you so how the dislocation so moves along the plane in metals and reaching the surface of our sample. And so you can see that dislocation motion requires the successive bumping of a half plane of atoms. Now it goes from left to right, and at the very bottom, when it reaches the surface of the material, we do have permanent change of material dimension. If you want, we do have plastic deformation. So again, so this movie shows you one more time that in order so to reach plastic deformation, so you don't need to destroy all bonds along the planes, let's say, of the slip step formation, but you need every time so the distortion of only so the bonds along one direction, which is normal to the plane of the edge deformation. So this illustration again shows you how the plastic deformation may occur in metals owing to the motion of the edge dislocation, and different, let's say, analogies such as caterpillar, for example, analogies explains you this effect. So next question is when the dislocation move and this slip occurs, so this motion and slip occurs along the direction with the, if you want to say, of the Burger vector. And of course, the shorter Burger vector, less energy we have to apply in order the slip takes place. And because of that, it is easy to understand that slip occurs along the most close packed planes and along the close packed directions. So now let's analyze different type of crystal structures, different type of crystal structure from the standpoint of these planes and their close packed planes and directions. For example, so here we have a FCC crystal structure. You can see it. And in the FCC crystal structure, as you can see here as well as you can see on the screen, the 111 plane are the close pack and the plane and hence the slip plane. So on the other hand, so we also can see that the shortest Burger vector here is the distance between the two close atoms along the diagonal of each plane of the cube. And from this standpoint, the 111 direction are the close pack direction, and this is slip direction. We do have four different type of 1-1 plane for each FCC crystal structure, and each of these planes it have let's say 110 slip direction. So in total we do have 12 slip systems in the FCC for the FCC crystal structure. Now, if you are talking about the HCP crystal structure, you will find out the basal planes here, which do have its plane 0001 plane, which are indeed the closed packed planes here. And along the basal planes, you have directions, 1, 1, minus 2, 0 direction, which are a basal slip direction here. So in total, we do have 3 let's say not intersected slip systems for the HCP crystal system. If you can see the BCC system, a BCC system does not have any closed pack planes. However, this system, of course, does have the planes and direction with highest atomic density. Now, for example, so the 110 plane and corresponding 111 direction here, or some others shown on this screen. So, and for sure, if we expect some slip in this system, slip should occur along these planes and directions with highest atomic density. So this table, in some sense, summarizes our conclusion, and based on this conclusion, we can make some predictions on the mechanical property of our material. Indeed, so because FCC system does have the largest number, 12, if you remember, largest number of the slip systems, so we can expect that this material should possess extremely high ductility. It means that it's easy to make a plastic deformation with this material, and indeed, aluminum, copper, iron, nickel, they do have this kind of crystal structure. For HCP system, we have only 3 slip systems. It means that we can expect that sigma yield and sigma tensile strength should be higher for this type of element, for this type of metals and alloys. And indeed, titanium, magnesium, so they do have in general higher mechanical property and higher brittleness. So while we of course can expect that for BCC system, it's even harder for the edge dislocation to move along them. That's why we have to expect higher tensile strengths, higher sigma yields, as well as lower ductility, and molybdenum and tungsten demonstrate this type of property. So the next screen just indeed shows you the result comparison of the result of the tensile strength experiment, which was made on the magnesium material and aluminum material. Just a reminder, magnesium has HCP structure. That's why we have to expect much more brittle type of behavior, while aluminum has FCC structure, and we have to expect the high ductility. And of course, the results shown on this slide nicely demonstrate this statement. So to conclude this part of our lecture, we have to admit that crystal structures defines the set of material properties, including mechanical properties such as sigma yield, sigma tensile strength, also some, of course, physical property, and we mentioned, let's say, color of our material for sure. And so because of that, by changing the crystal structure of materials which even do have similar makeup, similar chemical composition, we can control the plastic behavior of this material, the toughness of this material, ductility of this material, as well as their density and color. Thank you so much for your attention.